So we're going to start the afternoon session with Luca Tagliacozzo from University of Barcelona now, I understand. And he's going to talk about universal and robust phenomena in and out of equilibrium.
Thank you, Suki, very much. Thank you for inviting me here. I tried it 1 second ago. Maybe it was another one. I don't know. Okay, so it's just the pointer that doesn't work. Okay, no, it does work. Sorry. No, but it's fine. Okay, so this is, I guess it's a bit what everyone of us is trying to understand, and that it means we all have some approximate tool, and we would like to understand in which sense this approximate tool can give us some reliable prediction on phenomena that we are interested in. And a bit the focus of this talk is that actually, well, unless the phenomena you want to see is robust, then you have no chance. That's a bit the message of this talk. And it's actually a story that started very long ago when I moved into this tensor network business in 2007 at the University of Barcelona. And then there was a recent result that we obtained together with Philippe Corbeau. I think he will talk about it in the next few days when he has a talk. And I will focus on, so this is all for equilibrium, and today I will focus on the out of equilibrium scenario. And these are things that I obtained in a collaboration with the Laurent Sanchez Palencia group in France at Polytechnique. Jacopo Suraci is my PhD student, and Marco Piani was a colleague of mine when I was at Strathclyde. So let me start with a short background, and I actually want to flip the kind of main lore that we have heard up to now. And so basically, I'm going to tell you that tensor networks are good for low entangled states, as we all know. So there are theorems actually that tell us that, let me use the stick. So there are theorems that tell us that if we represent the Hilbert space like a ball, then there is a very small corner, and this is actually not up to scale, where states fulfill the so-called area law of entanglement. And in many cases, so we know of cases in which, despite the fact that the states fulfill the area law, there is not a good description of it in terms of tensor network. But in many cases, we believe that most of the states that fulfill the area law are good candidates to be described with tensor network. That's what we have heard until now. And then one would like to build ansatz that actually also ansatz of states that also fulfill this area law, and that can be optimized in order to give us interesting answer about the problem we want to study. But then if you follow this philosophy, for example, you would immediately rule out using infinite matrix product state to study 1D critical systems, because infinite matrix product state have a finite bond dimension, meaning that at some point the entanglement of a region would saturate to a finite value. But what we did back in 2007 was to study critical system nevertheless. So there was also a paper by Frank here in the audience, more or less at the same time. And then there have been a lot of, Nishino had a paper in '96. As always, it was too early for the community to appreciate him. And so basically, if you study what happens if you study a critical system with a matrix product state, here I show the size of the system and the precision in energy, and the different colors represent different bond dimension. And this black line is the prediction from conformal field theory that tells you that the ground state energy should converge to its actual value with a 1/n² correction. So this is the deviation of the ground state energy from the exact result. And so the exact finite size scaling would lie on this black curve. And now if you crank up your simulation and keep the bond dimension constant, you would see that for certain system size, your results are fine. Then your bond dimensional results start to deviate from the exact line, and they flatten up to these kind of results that somehow it's difficult to interpret what it means. But interestingly, if you now just plot the endpoints of these lines as a function of the inverse bond dimension, you see that there is a perfect scaling. And so somehow there is a kind of scaling appearing in terms of the bond dimension of your matrices. And actually, if you are clever enough and you scale things properly, you see there is perfect collapse of those curves into a single curve, meaning that universality is at play. And so somehow the message here is that no matter that your tensor network answer is wrong, it doesn't have the correct entanglement scaling, you can still extract all your universal information close to a critical point by performing an appropriate scaling analysis. So that's the message. And
connect this exponent to something, to other exponents?
Well, actually, Frank has an analytical result in which he shows that this extra crossover exponent that you get when you do the scaling is only function of a central charge in the 2D conformal field theory, and he has a formula on how to obtain that crossover exponent. And actually, then the other Frank had a way to simplify the calculation and get to the same results in a slightly simpler way a few years later. So there is some analytical prediction in 2 dimension at least. And now the question is what happens in 3 classical dimensions, 2 plus 1 quantum dimension. And for many years with Philippe we had discussed about that, because here the situation is different. PEPs do fulfill the area law. Critical states, at least a certain class of critical states where your model has isolated Dirac point, also have an entropy that fulfill the area law even at criticality. So the question is, will we see something similar or not? So we will see some kind of an effect of a finite bond dimension at the critical point, or will we be able to immediately find with very low bond dimension the correct critical state? And actually we don't know if we can find that finite bond dimension a critical state, but the numerics that I think Philippe will present in details show that at least in a certain model, there are clear finite size effects in the sense that your order parameter that you expect to vanish at the transition is very far from vanishing at finite bond dimension. Here is the value of the bond dimension of an iPEPS calculation. This is an interacting fermion model where the fermions hop on an Onicomb lattice. There is a critical point. So sorry, I should have introduced the model here. So here you have interaction between fermion on the nearest neighbor site. And there is a critical point. As you change the interaction, you go from a kind of charge density wave to a semi-metal phase at a certain value of V that was known by Monte Carlo simulation obtained here. So we knew that there was a critical point. And then Philippe did all the simulation with his iPEPS code, and we found these kind of finite bond dimension effects that we can exclude come from the fact that actually to contract a PEPS, you need to go down 1 dimension and use a kind of MPS-like techniques or one-dimensional techniques with this extra bond dimension that encode your one-dimensional truncation, the truncation that you do in your one-dimensional strategy. So as you see, he had carefully extrapolated as a function of this inverse bond dimension, but still find these huge effects. And so the message to that is that maybe entanglement is not really what we should focus on. So here we have a state that has the correct property. It's very hard to contract because it has the correct property of the entanglement. And we still see the similar phenomenology to what we see in 1 dimension where the state has the completely wrong scaling of entropies and things like that. So maybe there is something else there. And actually, in this specific context, it's very clear what's going on. And the idea is that we are very close to a critical point. Close to a critical point, the physics becomes universal. So no matter what you do, you can go into your RG framework and kind of project your approximation into scaling operators. And the scaling operator could be either relevant or irrelevant. It turned out that both in 1 and 2 dimensions, it seems that they are relevant. So they open a gap. So if you scale things properly, you can extract the critical properties of your system by doing such bond dimension scaling or finite correlation length scaling, if you want. So this is just it was just meant to be a motivation. So the idea is that, okay, we have found that no matter if we try to fight against this area law of entanglement with very complex tensor network ansatz, we still get somehow approximate results. They don't seem to come from the fact that we are approximating the contraction, but they seem to come really from the fact that we have a finite bond dimension. And so what about trying to look for a robust feature of the physics that we know that at some point would emerge, no matter if we are doing if we are introducing some approximation. And now this was all at equilibrium, and now the question is, what are these features out of equilibrium? And then the first things I wanted to point out is that maybe, I don't need to, but I wanted to show that at least in the simple tensor network setting, if you don't go to branching geometry or to strange thing, we have no way that we can hope we can encode the states that we get out of equilibrium with tensor networks. And the reason for that is the already celebrated paper by Cardy and Calabrese, when you now plot the entanglement entropy or a function of your complexity as a function of time, and you see that it increases linearly, typically out of equilibrium, and it saturates to something proportional to the volume. And so you expect really that your state at some point will become very entangled, and so at least your simple tensor network ansatz should fail to capture them as a full state. And the way in which you can explain this is by thinking that as you inject some, at least in translation invariant system, not localized, so kind of where the excitation are extended, you can think that your initial energy that you inject when you are out of equilibrium then get radiated in terms of pseudoparticles, and it's pseudoparticle spread, but they are correlated since they were produced in correlated region, and this leads this kind of a growth of entanglement. This was the explanation by Calabrese and Cardy back in 2006. And the question is there something robust in this phenomenon, for example? And the answer to that is actually yes. So if you generalize a bit what the pseudoparticles are to a kind of entangled scenario in which your ground state is entangled, then you can have these ansatz for excitation in which you just change your state locally and take momentum superposition of that. And then you immediately get that since you are saying that the low energy excitation have this form, then you have a dispersion relation for your low energy excitation. So the energy is function of the momentum of this excitation. And you have this kind of curves that encode the energy as a function of a momentum of your low energy excitation. And this curve has two main features that I will use in the following. One is the so-called group velocity that tells you how pseudoparticle with a certain energy and momentum would spread, and is given by the derivative of this curve at a certain momentum here, and this is defined here in green. And the other one is the phase velocity, that is just the ratio between the specific energy and a specific momentum. And so interestingly, what we tried to do, starting back in 2004, was to this I already said, sorry, was to try to take seriously this pseudoparticle picture and see what we could predict. And in particular, we were interested in this kind of, as I say, system in which a pseudoparticle should exist because they are translation invariant, so we expect that the excitation are momentum state. And for example, you could think of it as the Bose Hubbard model with these so this is a lattice with position r and r prime, and these are operators that tell you that a boson is created at a certain place r and destroyed at a certain place r prime, meaning it hops from r to r prime, and then when they meet, they interact with certain energy, for example. But this is completely general, and it can be applied to any Hamiltonian that can be written in such a way with two-body interactions. And actually, the first thing that we did was to study certain quenches. At the beginning, we would study local quenches where you actually inject very little energy into the system, and so you expect that the dynamics is actually confined to the low energy subspace of your system, and so you expect this pseudoparticle to give you a nice description. And then we would do something, your initial state, and then change the Hamiltonian such that the system would go out of equilibrium. And here, for example, I plot the expectation value of a certain operator as a function of the position of my system. It's a 1D chain, and as a function of time also. And so what we found is actually that this pseudo-particle picture was very general and allow us to predict quantitatively certain feature. And in particular, so in this paper here, we were able to see how this causal spread of correlation would break up with long-range interaction. So if we now take a system that has long-range interaction, one question is how far the system is still local, and then this depends on this exponent alpha. So this system has hopping at every possible distance, but the hopping is weighted by the inverse power law with some exponent alpha. And then here you see three different ranges of parameters. So for alpha equal to 3, you see these are numerical calculation with MPS, and these are kind of pseudo-particle approximations, so mean field calculation based on the pseudo-particle picture. You see that both at long and short time, so these allow you to go to arbitrary long time because it's kind of an analytical calculation. This is limited again to relatively short time because the entanglement grows. But interestingly, if you would zoom the two, they are completely equivalent, so there is no difference. And so somehow you could use a very approximate technique to predict what's happening in your system. And interestingly, these approximate techniques allowed you to discern three different regimes, one that we call short range, one that we call intermediate long range, and one that we call completely long range, based on the fact that if you just look at the dispersion relation of the pseudoparticle, so without doing any dynamics, just looking at the dispersion relation, you can see that at certain point it develops a cusp, so meaning that the dispersion relation becomes singular, and so the group velocity diverges, and in certain other point, when alpha keep decreasing, it directly diverges, so there are kind of let's say a large number of modes that become superluminal, if you want. And then this is shown in this plot here, where you see that now the logarithm of the maximal velocity as a function of the system side, when the system is short range, it doesn't depend on the system sides. When the system is in this intermediate regime, it does depend on the system side. So larger system have larger maximal velocity here. But still, if you divide by the sides, so you get an inverse time, you see that still larger system have smaller inverse time. So the perturbation take longer to get to the boundary than in smaller system. But at some point at one, the two things cross, right? And that's what actually these three different regimes mean in terms of the pseudoparticle. So we have a clear analytical picture that doesn't require any strong numerical simulation, and actually it's confirmed by the numerical simulation. And so you could take it further and try to generalize this approach to more interesting correlation function, and that's what we did with the group in Paris, so Laurent Sanchez Palencia, and we, for example, found that you could engineer quench in which, depending on the ratio between group and phase velocity, your kind of correlation cone has a certain shape, but then you have an inner structure of maxima and minima inside your correlation cone that follow the phase velocity rather than the group velocity at a certain given momentum. So for example, if you are doing an experiment and you are trying to measure these things, you have to be very careful that you are actually measuring this correlation edge and not the maxima and minima. And luckily enough, the experiments that have been done are in the regime in which phase velocity and group velocity almost coincide, but it has been already an accident. So the experiment all measures somehow this maxima of the correlation rather than the correlation edge. And here you see again, these are simulation made with a matrix Proudhon state, and these lines are the mean field calculation, and these are the velocity that we extract by fitting our numerical data with some fitting thing, and you see that they coincide pretty well with the mean field results in a lot of quench scenarios. So here I'm quenching in the superfluid phase from u times n equal to j to u times n equal to some fraction of j, and here this fraction goes from 0.5 to 3, and in all these cases, this is a global quench, so it's a global quench inside the same phase, and it's still amazing how well the pseudoparticle description at the mean field level is accurate with respect to the full dynamics. And it's also to me a bit of a mystery that happens. So this was published here, and here is the opposite case in which now the group velocity is actually lower than the phase velocity. And so yes, you see these evanescent cones coming out of your correlation edge. Okay, and then the last thing is, okay, we have seen that somehow at short time the propagation of correlation seems very universal and can be captured with very simple model. And actually in the group of Frank Westerreiter, they improved on this simple model and went to construct this pseudoparticle excitation on matrix flow state, and they found very similar results. And now the question is there anything robust we can predict at long time? And this is the subject of Jacopo PhD. There have been other works by Frank, here other works in the literature going a bit along the same direction. And here the idea is really that if you look at what happens at long time, so you have this particle propagating, and then if you cut, so this is again space and entropy, and now it's at a fixed time in which a pseudoparticle have propagated a bit, and so you have this entropy profile, and if you cut it here, you see that the entropy profile hasn't changed much, but it has been somehow lifted by the fact that you have an entangled pair. And actually, so you could say, okay, but then when the two pseudoparticles have passed, what happened, and you see that actually locally, you still have a very similar density profile that you had at the beginning. And so it seems like this long-range entanglement shouldn't be very relevant for the local physics. And so actually one natural question to ask is, can we find a local description of the dynamics? So forget about describing the full state, but let's just try to focus on local properties and see if we can describe the out of equilibrium dynamics by only focusing on local properties. And there are good reasons to think that we can do that. First of all, because if your system thermalizes, at the end, the only thing that is relevant is the energy density. And the energy density, if your Hamiltonian is local, is contained in the expectation value of local operators. And so somehow the thermalizing dynamics should be insensitive to the long distance properties of the state. At least the final state should be. But one of the things that you have to realize is that if you want to do it in a systematic way, there must be a way to convert this entanglement between distant pseudoparticles into mixture. Because anyway, when you will look at the system locally, your partner would be very far away and you will have anyway traced over it. And so this entanglement will just show up as a mixture in your calculation. So the idea is that you can set up such an algorithm with tensor network, you do the evolution for a certain time, then you look for a mixed state that locally is indistinguishable from your pure state, and then once you have started with this mixed state, then you evolve it again and find another mixed state with a treatable Schmidt operator Schmidt rank, such that, again, at a certain length scale, they are indistinguishable. And so people have implemented the things, for example, Zaltel did with G. Raphael in a tensor network context. And we wanted to understand first, before implementing this, what you would expect. And the way we did it was to simulate a fermionic system with the same strategy. 2 minutes, 1 minute, 2 minutes. Okay, fermionic system with the same strategy. So the free fermions are described by correlation matrices, as we already heard. And so everything can be computed exactly in this case, and the correlation matrices are only 2 times the size of the system, so you map an exponentially hard problem into a polynomially large, and you can actually perform the evolution and look at what happened. And so typically we consider a free fermionic Hamiltonian, whose most general form is this one, and now the idea is that we perform an evolution for a certain time. Then even if you start, so this is the correlation matrix. So the correlation spread, as we said, so the element of say you started with a very shortly correlated state, so only correlation along the diagonal. Then as the time goes by, your correlation increase. And then at some point you would like to erase the correlation beyond a certain distance because you are only interested in the local physics. And it's not even clear if you can do it in a physical way, but I don't have time to discuss it here. But anyway, so we checked that, and it turns out that there is a way in which you can do it in a physical way, because it's not clear that a certain correlation matrix represents a physical state. But anyway, let's assume that this is settled. And now the question is, what happens? And so you perform a quench using your Ising model, and here, let's say, this is a kind of a dot of the transition, so we are here in the same phase. I never remember if you call it order or disorder, but anyway, we are on the certain sides of the transition from theta pi divided by 4 plus 0.1 to pi divided by 4 plus 0.3. And here are the results. So here is a bit dense. So let's say the blue line here, that is this line here, is the results for a very, very large system that we can take it as in the thermodynamic limit for arbitrarily large time. Everything else is for smaller systems, so it is a 20-side system. M represents this truncation parameter in which we decide how many local and non-local correlation we keep. So M equal infinity means that the evolution is exact. And we compare it with the system of size 200. So the system of size 200 is the red one, the exact one, and it relaxes, and then at around some times its length, it has a recurrence, as we expect, because it's a finite size system. And then we compare the evolution of these two systems exact. This is our exact benchmark, and this is our approximation. And I just show one value of the approximation because everything gets messy, but morally they are all very similar. And this is the green line. So you see that once we do these things, our system takes much longer to relax than the 200 side that was relaxing around here, but it doesn't show any recurrence, and it eventually relaxes more or less to the same correct value. Here is a zoom of the first 1,000 cycles where you see a bit closer what's going on. That when the red systems start to have recurrence, the green stays close to the equilibration value. And then you can ask yourself, what is the equilibration rate? And with this, I'm almost done. And you can find that actually both of them are power laws as a function of the time. So this is the exact one. And this is is the opposite. So this is the exact one, and this is our truncated one. And you can even ask yourself, how fast does my equilibrium state converge to the correct diagonal ensemble equilibrium state? And it turns out that is exponentially fast with a power. So the exponent of minus m to some power gamma. So this is the kind of a fit of the gamma. So it's faster than exponential. And then you can ask yourself, is my approximation physical? So am I describing physical state? And you can see that actually, if your m is above 20, actually that's always the case. And so the approximation works. So basically, what I have shown is that, with this I conclude, what I've shown is that using free fermions and you can somehow benchmark tensor network ideas, and these tensor network ideas seems to suggest that there may be a way to locally simulate the out of equilibrium dynamics and extract also kind of power law convergence to equilibrium by focusing on local properties rather than global properties. And with this, I conclude.
Thanks, Luca. So we have time for maybe one quick question.
So I'm wondering, like, have you checked what happens as you change the criteria for local equilibration, right? Because you always have a choice to pick, like, what kind of operators you want to match between the exact state that you evolved, or like the state that you want, and the state that you approximate, right? Or like you use as a proxy. So for example, you might want to include correlations between sides that are like 2 apart or like maybe 10 apart, right?
Yes, so for me this is my M. Let me fastly go back. So you see, my M says that I'm taking into account the correlation, all the correlation up to M. In this case, the system is Gaussian, so by taking into account all the two-body correlation, that's it. I don't need to take anything more into account. And this is for the criterion of what I want to conserve. So, and morally, this is this number of sides, so the reduced density matrix of certain sides, right? So M here would be 3, for example, but I could take M4, 5, 6, and this is just a parameter, an extra parameter in the algorithm. And now the answer is, if I take M equal 3 or M equal 20, how many sides operator I can trust, right? So, because I think you have to think that morally, you will end up in a thermal state. There is a certain thermal correlation length. And so if you're interested in one site operator, you still have to fatten your region with a number of sites that is of the order of the correlation length in your thermal state. So somehow you know that if you have a not so high temperature, you need maybe to have a larger cell here to get the things right, at least at equilibrium. And then the question is, how does these sides influence the way in which you approach equilibrium? And in our case, we tried several quenches and things. It didn't seem to affect the rate at which you approach the equilibrium. It seems it affects the final value that is exponentially close to the correct one, and it goes down exponentially with the size of this support, but at least not the slope of the power law. So that would be what we find. We don't have an analytical understanding of that, so we have just numerical evidences. These states are Gaussian, yes. We believe that that's actually a limitation in the sense that we know that the Gaussian states do not equilibrate to a Gibbs ensemble, but to a generalized Gibbs ensemble. But there are these papers by Fagotti and Esler in which they show that truncated version of the Gibbs ensemble are exponentially close to the correct generalized Gibbs ensemble. And we believe that that's where this exponential difference arises in the equilibration value. So we think that in principle with the non-interacting system, things should even be easier, because in some sense, there is a well-defined Gibbs ensemble, and you don't have to care about non-local conserved quantities, and everything is conserved locally. So.
Okay, one last question.
But I understood that if you have such free systems and you actually look at the true thermalization, you in the middle of at short times you actually create a huge amount of entanglement, and then actually only at later times you relax to something that for which the mutual information satisfies an area law. So I don't understand how you would be able to capture actually this intermediate regime at all using your.
So actually, we have the plots of the entanglement, and at least in the scenario we have considered, so in the Ising model quenched from one point to the other, the entanglement is monotonically increasing, and then it starts to oscillate only due to the recurrence effects of the fact that you have a finite system. So it goes into a volume law, but the point is that here, since you have a mixed state, you can directly have correlation that somehow you could have an identity that has a volume law of correlation. So somehow you are converting entanglement.
No, but I'm talking about the mutual information, and the mutual information becomes very large and then decreases again for long times.
Okay, I haven't checked the mutual information. I just checked the bipartite. So mutual information among two regions. Yes. Well, actually, I don't expect that, because you would expect a typical cone, right? So if you have two regions that are separated, they are not entangled until the pseudoparticle arrive. They become entangled for some short times, and the effect is quite small. And then, as the pseudoparticle fly away, they'll go back to the kind of average thing.
You're talking about two different things. You're talking about a local quench.
No. This is global. This is completely global. So it's a quench even between two phases. So this is something that has been studied in conformal field theory. There is a negativity plot. Tony, Calabrese, and Koser, I think, they plotted the negativity as a function of time between two blocks, and actually you just have this kind of like this shape. So you wait, it grows linearly, it decreases, and it's gone.
It's expected, except for the thermal value of very long time.
Yes.
All right, so let's thank Luca again.